So dear students, welcome to lecture 16. Today we are going to talk about yet another heterocyclic compound, that is quinoline. Before beginning this discussion on quinoline, let me ask you a question. Did you ever get malaria, or you know somebody who contracted malaria? And do you know what are the drugs that are prescribed in this category? So we will try to find some of the answers to these questions today. So quinoline is a liquid and it is present obtained from coal tar. It is has a low melting point, but it boils at a higher boiling point of 273 degrees Celsius. Quinoline is a compound which contains a benzene ring fused with a pyridine ring. That means benzene and pyridine ring are fused together to give us that kind of structure. Whenever you see that framework, it is known as quinoline or quinoline derivative, and it is generally used to synthesize dyes and other compounds which have pesticidal or anti-malarial activity. Especially two compounds here are worth mentioning, that is quinine. This is naturally derived from cinchona bark, and it has this quinoline framework, but it has some other substituents on the C4 carbon and C7 carbon, and this compound has antibacterial properties. Then there is another molecule known as chloroquine, which also has the quinoline framework, and it is somewhat cyclic open chain structure on the substituted carbon group, and this is also has antimalarial properties. Now let us turn toward the synthesis of these important quinoline derivatives. A number of named reactions allow us to synthesize quinoline and its derivatives. So let us study them one by one. So the first important synthesis method that we want to study is the crop synthesis. In this crop synthesis, aniline is reacted with a alpha beta unsaturated carbonyl compound. An alpha beta unsaturated carbonyl compound like acreolin may be used here. So aniline, being a nucleophilic compound, reacts with the electrophilic alpha beta unsaturated compound. So the lone pairs on the nitrogen attack on this carbon. This results in the shift of this double bond to this place, and the oxygen gets a negative charge. But soon the oxygen can handle the negative charge but doesn't like it for too much, so it then we can think of this like the negative charge coming back to the carbon and this double bond moving back to the original position. But in so a carbon nitrogen bond has already formed. So in this species it can further rearrange to shift the proton from nitrogen to oxygen. It will give us this positively charged intermediate, and this carbon, being electrophilic, is then attacked by the pi cloud of the benzene ring. This thus leading to a carbon-carbon bond that we see here. But in this attack, a positive charge is left on this carbon, and this is then neutralized by the adjacent nitrogen atom. And therefore we can rewrite this structure like this, in which the nitrogen is getting the positive charge and sharing its lone pair of electrons with the carbon. Now this molecule undergoes a dehydration step and loses a molecule of water to give us this quinoline like framework in which the nitrogen is positively charged. This proton is then lost to the solvent and we get quinoline. So this is a crop synthesis in which alpha beta carbonyl compound has reacted with aniline, and through a series of intramolecular rearrangements and reactions it has given us quinoline. Now another method of synthesizing Friedlander's synthesis. In this, aminoaldehyde is condensed with acetaldehyde in basic conditions. So this is the acetaldehyde. It is condensed with aminobenzaldehyde, and here we see that again the nucleophilic character of the aniline comes into the picture, and it attacks the carbonyl carbon, and there is a rearrangement then takes place. Shifting of this double bond takes place to give us that Schiff's base. This then is attacked by the hydroxide ion. It will abstract this proton present here, and it will generate a carbon anion here. This carbon anion is very adjacent to a existing carbonyl group. Therefore they react in a nucleophile electrophile reaction and form a carbon-carbon bond. Because this forms in the presence of water, the water gives a proton to this oxygen. This then further can lose a molecule of water and give us the quinoline. Friedlander's synthesis, aminobenzaldehydes react with carbonyl compounds and through a series of intermolecular reactions it gives us quinoline. And similarly we can use substituted amino benzaldehyde derivatives, and instead of the acetaldehyde we could have complex carbonyl compounds, so it will give us substituted quinoline derivatives where the X, Y and Z substituent might be coming from the corresponding carbonyl and the aldehyde groups. Another well-known method is the Conrad-Limpage synthesis. In this, condensation takes place between the primary aromatic amine like aniline and beta ketoesters. So this is an ester, alpha and beta. So at the beta position there is a keto group present. Therefore these compounds are known as beta ketoesters. Therefore these compounds react with each other. First nucleophilic attack from the nitrogen will take place on the carbonyl compound, and a set of rearrangement and loss of water molecule will take place to give us that compound in amine. This is then heated at 250 degrees Celsius. That results in the attack of this bonding pair onto the carbonyl carbon, and then for cyclization takes place, a new carbon-carbon bond forms, and this molecule then tautomerizes to give us the 2,4 substituted quinoline derivative. There is another way we can form quinolines, that is by ring expansion of indoles, and in this indole is reacted with a dichloromethane under basic conditions. As you know, dichloromethane under strongly basic conditions will generate carbenes. So this carbene is formed, in which carbon is highly electron deficient. It adds to this carbon-carbon double bond and a bicyclic structure forms. But because of its instability, it soon loses the chloride molecule, and the nitrogen atom forms a carbon-nitrogen bond, and this rearrangement takes place. This carbon-carbon bond is broken and a new carbon-carbon bond between these two carbons forms, thus giving us a quinoline derivative. Now let us move towards the reactions of quinolines. Quinolines are basic in nature because they have a nucleophilic nitrogen which can accept protons, and therefore such nucleophilic nitrogen centers we know react with alkyl halides, but in this case they will form salts. They will form quaternary ammonium salts of quinoline because the nitrogen is already tertiary here. When it reacts with the alkyl halide in an SN2 fashion, it gives us the quaternary ammonium salt. Then in the next react, quinoline being aromatic heterocyclic compound, it also tends to undergo electrophilic substitution reactions easily than addition reactions. So electrophilic aromatic substitution can give us 8 substituted quinoline derivatives. So we will study the sulfonation and nitration of these compounds. If we take a look at quinoline sulfonation, concentrated sulfuric acid conditions in the presence of sulfur trioxide, sulfonation takes place at the 8th position, but this is a kinetic product in which means that at lower temperature 8 substituted sulfonyl, which means that at lower temperatures 8 substituted sulfonic acid derivatives will form, but when these are heated at high temperatures they will exchange the sulfonyl group to give us the 6 quinoline sulfonic acid derivative. So here we can number 1, 2, 3, 4, 5 and 6. Therefore this compound is known as 6 quinoline sulfonic acid, and it is a thermodynamic product because it forms, the reaction mixture is allowed to equilibrate. Under kinetic conditions the reaction is not equilibrated. At low temperatures whatever energy is available, that is used to form products. Such products are known as kinetic products, but when you supply a lot of time and energy, the products that are formed are known as thermodynamic products. So let us further study the reactions of quinolines and continue the electrophilic aromatic substitution. As with any other aromatic compounds, bromination can take place and it can give us a mixture of 3 and 5 bromoquinoline derivatives. At higher temperatures it will give us the thermodynamic product, that is 5 bromoquinoline derivative. Then continuing reactions of quinoline, we find that nucleophilic aromatic substitution can take place, and as we have studied with pyridine and other compounds, nucleophilic substitution can take place to give us quinoline two amine derivatives in which the Chichibabin type reaction takes place. But nucleophiles, this is a nitrogen centered nucleophile, but carbon centered nucleophiles can also react. Here is an example of a carbon centered nucleophile, that is 2-methoxyphenyl lithium, in which there is a carbon lithium bond in which carbon has a negative charge on it, and this is the sp2 hybridized orbital which is sharing bonding electrons with lithium. But because of the electropositivity of the lithium, the carbon has a negative charge, and this negatively charged nucleophile can attack on the quinoline ring at the C2 position. Once that attacks, the nitrogen lithium coordination takes place and we get the addition compound. This can react with water and you will get a hydrogen here. So we get the addition product, nucleophile adds here, but to retain the aromaticity of this ring, a proton is lost from here. To retain the aromaticity of ring cyclization takes place to give us 2-methoxyphenyl derivatives of quinoline. Here is another example of the nucleophilic aromatic substitution on quinoline. This time we are using the butyl lithium as a nucleophile. So carbon lithium bond is present here, and carbon is nucleophilic and negatively charged in the butyl lithium. This attacks on the C2 position of the quinoline ring, and similar reaction takes place with water. We get a hydrogen here, and to maintain the aromaticity of the ring, oxidation of the ring takes place and gives us the quinoline derivative. Now we will see in next lectures, we will study free radicals. Thank you.